Okay, great. It's great to be here. All right, the first thing I'm going to, at the top, it says active optimization for embedded learning systems. There's a word Bayesian optimization that gets used a lot. And what I'm going to talk about is pretty much that. I just use the word active optimization because there's no reason it has to be Bayesian. It can be. So just so you're not confused there. So what am I going to do? Why am I interested in that? And what am I doing at this particular workshop? Well, the aspect of transportation I'm interested in is vehicle autonomy, so self-driving cars. And what I'm going to do is start with just a little background, a little history of that to get to where we are now at Uber ATC. And then I'm going to go into active optimization and some of the challenges I see there and some of the things that we're doing about it. So let's just start with some old history, right? It turns out self-driving vehicles have been around for quite a while. Some people may not realize that, but all the way back in the 80s, for example, at CMU, they had this van driving around. And it's a van because it needs that much space to hold all the compute that it's using to drive around. And of course, the performance of there was not much, right? This was the era of just keep the video running in case something good happens so we can show it to everybody, right? But it goes back a long ways. So in some ways, that particular project, in some ways, you might say, culminated in the No Hands Across America drive, which happened in 1995. And so that was a drive from Pittsburgh to LA that was 98% autonomous. And its longest stretch had 70 miles with no intervention at all. And this one was pretty simple, right? It's just a camera. Didn't really know where it was going or what it was doing, but it knew how to stay in a lane. That's what it knew how to do. And the other thing that was cool about that one is that one happened during the previous incarnation of deep learning. So we all know it's gone through several rebirths and deaths. This is from the previous one, and that's what it used. So that was pretty exciting. You know what happened later? Oops, is that going to play? It is going to play. Okay, so we wanted to do better than that, right? So in the 2000s, this is Crusher. And so what are the things that got added here? Well, this thing actually knows where it is. It has GPS, and it also knows where it's going. It's got waypoints at about 2 kilometer spacing. It's also got a little more sensors. It can see some LiDAR. But it's not really doing a lot more than that. It doesn't have a map. It doesn't have any concept of an object. It just sees these static things that are in its way and just tries to plan around these things that seem to be in its way. So that was a step forward. And of course, maybe the big step forward was the DARPA Grand Challenges. And so these were autonomous vehicles that were driving in cities. This was in 2007, fully autonomous driving. And this is when things switched a little bit. These had good maps, where here good maps means it's got a 3D model of the world it's driving in. It knows where it is, not only from GPS, but it actually sees everything else around it. And of course, the Velodynes are here for the LiDAR, but it has the other sensors as well. Of course, most importantly, CMU wins. That's always good. But maybe the real milestone was here. The Google car project essentially began here. They looked at this and said, you know, the method that CMU used and many of the other top performers in this, which is essentially what I've described in the bullets, it kind of works. Let's go do that for real. So that was a real milestone in self-driving cars. Of course, CMU also concluded that things were ready to go. And what they did is partnered with Caterpillar in order to make some autonomous vehicles to drive around their mines. I don't have a video of that, but they also partnered with various farm equipment manufacturers and really got into a lot of vehicles there. And so the cool thing about this is that the real benefit was just safety and preventing costly mistakes. So this truck here is enormous, right? You guys have seen these before. So if you're driving a regular pickup truck around and you drive over something you shouldn't, probably you pop the tire or something and you've got to go change the tire, right? If you drive this where it shouldn't, it probably drove over that pickup truck. And the price of these tires is enormously expensive. And so just getting these automated and having a central operations is a big plus for the operation of the mine. Okay, great. So that was leading up to this. And of course, what happened in 2015? Uber came and opened a lab in Pittsburgh to look at vehicle technologies and mapping safety and autonomy. And so many of the faces are there would be familiar to you as some of the CMU people who were involved in doing some of the projects that I showed before that. This is a picture of our car. So this is the thing we would like to drive around by itself, and so you can see just by looking at it, it's got the LiDAR scanner on the top, and it's got a whole array of cameras around the top also. Of course, it's got GPS and radars and the other things you would put on a car, and this is the thing that we would like to be able to drive around autonomously. And so what I'm going to do now is show you what in any other world would be a very boring video. This is something we see every day. But when you think about self-driving cars, this takes on new meaning because what's in that video is absolute chaos. There's vehicles moving all over the place. There's people moving all over the place. There's marks all over the road. There are tons of other marks that are completely irrelevant. You'll see bikes go by once in a while. There are various little cues like traffic signals and signs that actually do matter. And of course, the environment is different everywhere you go. A streetcar will pass us at some point. There's just chaos going on there. And so what does that mean? There's a lot of, the systems as I described them before, they already sound pretty complex, but they really sound complex when you look at the videos they're supposed to navigate and realize that there is a ton of engineering and a ton of parameters in there that are important. The other cool thing is, we live in interesting times, right? The world is changing. Uber's not the only one pursuing this. Lots of companies are interested in this, which means really the automotive market is undergoing changes. And what does that mean? We have a need and an opportunity. We're going to have more computing power, more data, more stuff available on the car, less price sensitivity to put it on there, and even changing product specs. It's going to be more and more that safety and efficient really are the drivers that are most important here in comparison to the traditional focus on brand and style. The real thing for this talk, though, is all this increased system complexity means that learning and active optimization is going to become widespread. It's the only way you can do it. The system's just too complex. It's going to be learning on board, it's going to be learning off board, it's going to be never ending. And so these learning algorithms are what's going to make this work or not work. So that's what I really want to talk about in this talk, how we're going to make that happen. So, okay, enough vehicle autonomy for now. Let's now come to active optimization. So those of you who are in this area will recognize this, but for those who aren't, I'll go right back to the beginning. So what is active optimization? It means there's some unknown black box function like this one here. Somewhere it's got a maximum, and it turns out that doing evaluations of this function are quite expensive, and maybe you can't even get gradients. So you would like to do global optimization of this function with as few experiments as possible. And so, just for context, so you can think about this as a parameter somewhere on that car, maybe how aggressively it steers. And you would like to set that parameter so that it's the safest and most efficient car out there. Okay, so what is this? It has lots of names. This idea has been around for a while. It's called design of experiments by statisticians usually. Bayesian optimization I mentioned before. People use basically the same algorithms for bandit algorithms. There's an active search and optimization. And so what are examples of this? I'm excited by tuning these cars, but another area where there's a lot of excitement is just tuning the hyperparameters of supervised learning algorithms like deep networks. It's very expensive to do cross-validation on those things, and so choosing those hyperparameters already is something you would like to do more efficiently. Of course, the cars themselves are physical systems, so that's an obvious expensive experiment. But there are lots of other things that get tested in simulation, whether it's stereo algorithms or control parameters or other things that you can simulate. Even in the sciences, you simulate things to test your model. So those are the kinds of things that are expensive to evaluate. They're not convex. You may not get gradients, but we want to optimize them. Let's see. This is just, again, for people that are not too familiar with this area. There's a few different varieties of this. So people who are familiar with bandit algorithms, that's one variety of that. Usually with a bandit algorithm, you think about cumulative regret. So your score is how you do over the whole course of the optimization. Other things focus more on simple regret. Those are the optimization problems, which means you can run as many bad experiments as you want the whole time. It's fine. You only get scored on whatever the best value you found while you were experimenting. And of course, there are other versions where you're just searching for good examples, and you get scored on how often you find a good example. I put all these up here just to show you that they're all very connected to each other. For the rest of the talk, I'm mostly going to ignore the distinctions here and just talk about them generically as being the same. Okay, so what's our framework? It's common to use a Gaussian process. So what you do is you take the data points that you already have. You model them with this surrogate function, with this Gaussian process. That's your current understanding of this function you're trying to optimize. And so what are the key things about a Gaussian process? Most of you know these already, but the important things are it gives you nice confidence intervals on the function that you're trying to model. You know where you know it and where you don't know it. And also the inference, although it's expensive, it is closed form. So that's another plus. Okay, so how's this going to work? So we have this unknown function. We've observed these points where the x's are so far. We use the Gaussian process to obtain some posterior. So here's a bunch of samples from this posterior. Given the data points we've observed, these are a distribution of possible functions that might be the real one we're dealing with right now. And then what do? We define an acquisition function. So that acquisition function is defined from the distribution of functions we have on the Gaussian process. And what we're going to do is maximize that acquisition function, and that's the place where we want to do the next experiment. So just in this particular example, that place where the experiment is chosen seems like a reasonable choice because the function looks kind of high there, and there's also some uncertainty there. So probably that's a good opportunity to maybe find an even better point than we've already found. Okay, but let's be more specific. What are examples of acquisition functions? One is the UCB acquisition function. It stands for upper confidence bound. And what that means is pretty much just what I was saying. You look at the distributions of this function and you look at an upper confidence bound on the function and you pick the maximum of that. So of course, it's very intuitive, right? The maximum of that is somewhere that you think the function is probably high and there's uncertainty about the function, so you're going to learn something. There are many other variants. Expected improvement is a common one. If you have a best result you've achieved so far, it's easy to do this integral and compute an expectation of how much you might improve based on each experiment you might do. There's others, Thompson sampling and Gittins indices are other alternatives for acquisition functions. But they have the same rough intuition. You want to pick places that probably are good, but you're not certain, so you'll learn something from them. Okay, so here's the whole algorithm. You model it with a Gaussian process, you compute your acquisition function, you optimize the acquisition function. That's cheap because you're just doing that on the GP model. Then you run the experiment that was selected by it and you repeat. So here it is. Let's look at an example of this happening. So you start, you have no data. So you just have this sort of flat band where this function might be. You pick a point there, they're all the same. What does that do? This gives you a new model, a new upper confidence bound. Okay, now you have that. Now you pick a point on the far left. Okay, you get that experiment. That gives you this now upper confidence bound. Okay, now you pick one on the right. That gives you this. Now you have a new upper confidence bound that picks one there, and it goes like this, and so on, until you get to the end where you've done a pretty good job of modeling this function. And you can see that when you get to the end here, it's done what we wanted. It's explored the whole function, but it's spent most of its experiments near the peaks trying to find the very best point. So that's how that works. Okay, that's fun to do with 1D functions, but of course 1D functions are pretty easy to optimize anyway. Pretty much anything works on a 1D function. What happens if you want to do something real? So let me jump over. This is transportation that's not particularly large or not particularly fast, but it's still an interesting thing to observe here. So this is a robot snake. It's about this big. It has 16 joints, and it would like to crawl as fast as it can and do other things. So it's got a gait that's a bunch of sine waves that you can parameterize, and we'd like this thing to move fast, but it's expensive to do experiments because all the dynamics are nonlinear and based on friction, so they're hard to model. The only way you can get this snake moving is to run some real experiments. And so we'd like to use active optimization to run those experiments. And so that's exactly what we did. So I'll just flash you through some videos here just for fun. This is a human-tuned Sidewinder. This is what it does after 40 tries of active optimization in a three-dimensional space. So it's obviously making a lot of progress there. This one is fun. This is a very short video because we could run this all day and the video looks pretty much exactly like that. This thing is just not getting anywhere up that ramp. But again, 40 experiments of this active optimization, and this thing has figured out how to do something interesting, which is every so often it sort of twists itself over so that it doesn't fall backwards on itself, and it's actually able to climb this ramp that you can see. Actually, the ramp is slippery. It's sliding on the ramp, but it's still able to find the right motion to crawl up there, which is pretty exciting. So, okay, that's fine. Those are these parameterized gaits, but maybe we'd like to do something even harder with the snake. So it turns out this snake, what it's really designed for is disaster recovery. So when there's an earthquake, it's meant to go crawling through the rubble and look for survivors. And so often what it has to do is climb over some obstacle. And this cannot be achieved just by putting some sine waves through it. It actually needs a choreographed sequence of motions to go through. So this is quite a challenging optimization problem. So what did we do? We sent something up at the museum in Chicago. We put up a master-slave thing and made it a puzzle for the kids. We call this, instead of crowdsourcing, this is kid sourcing. And what happens is the person shows up, there's two snakes there, and they're holding one of them, and whatever they turn the joints to, the other snake will make that same motion in their joints. And the idea is it's a puzzle for them to figure out how to get the snake over the obstacle. Why do we want it? Because we want to find some parameterized set of motion primitives that we can use as our primitives that we're now going to run active optimization on. So that's why we did it. And so what happens? Now you can watch this snake as it learns to climb over obstacles. And this is our first crack at this one, and it's not going well. You can see it's thrashing around and it's having a rough time learning. So what we discovered here, let's see if I can, see if I can scroll this ahead a little bit. We concluded, well, let's give it an easy obstacle like the one at the museum. We're pretty sure it can figure out how to get over that, because even though it's hard, some of the kids managed to get the snake over that. So what we did is we started it with this, and then as we go, we increase the difficulty of it. And we actually put the difficulty of the obstacle in the Gaussian process model, so it's able to put this together. And what I'm going to do here, if I can, is skip this thing ahead. I think I'm going to skip it ahead. Oh no. Oh, that's a bummer. Okay. Well, maybe this is not gonna go too long. I wanted to skip you right to the end so you can see what it's finally able to achieve, but apparently I can't scroll it, so we're going to have to watch for a little while here. One of the things you'll notice as it goes that it's actually figured out something along the way that's interesting. When it started, it can sort of just do this and sort of flop over the thing. It's not too hard. Along the way, it figures out that the only way to get over a high obstacle is it has to do like a Fosbury flop. It has to lean back over the obstacle like this, and that's the only way it makes it over the high one. And so you'll see it here doing that. That's what it looks like in real time. So it's pretty cool that it's able to figure that out as a result of this optimization algorithm. Okay, so I think maybe it even does one higher, but that's fine. Okay, great. Okay, we have an active optimization algorithm. We can make real physical systems go well with a manageable number of experiments. Awesome. Okay, that's great. Here's the bad news. We had to do that thing in the museum so we could get a parameterized set of bases that was only 3, so that we could search a 3-dimensional space. I can promise you that we would love to have that snake optimized in a 20-dimensional space. It's got way more degrees of freedom than that. And I can promise you even more that even 20 is a tiny fraction of the number of parameters on our cars that we want to drive around, right? We want to optimize a much bigger space than that. And this is where the problem comes in. So theoretically, we already know that the algorithm to run optimization here, it scales exponentially in the dimensionality of the space in terms of the number of samples you're going to need to optimize the space. And for that matter, even we think of optimizing the acquisition function as kind of a freebie because you're just doing it on a GP, but even finding the optimization of the acquisition function is hard. So things are just not going to go to high dimensions, even though that's what we need to solve real problems. And so what are we going to do about that? Okay, this is what I already mentioned. We've got 2 challenges to deal with. One is the statistical challenge, that we need too many experiments to optimize a high-dimensional space. And the other is the computational challenge, that just optimizing the acquisition function can be unreasonably expensive. So what are the approaches to that? Well, there's a whole thread of work that works on the assumption, okay, you've got a large dimensional space, but let's suppose the real function is somewhere in a small dimensional space buried in there. So essentially, this is an easy problem hiding in a large space. And so there's a different number of things. One is you try to find that smaller set of variables and then run a classic optimization algorithm. Another is you try to find a lower dimensional subspace. Another one is, for some assumptions, you don't even have to find the subspace. You can take a random projection and you'll be guaranteed that the optimum is in that, because the optimum itself exists in a high dimensional space. So there's lots of things like that. The advantage of those is you get tractable optimization in high dimensional spaces. The disadvantage is, well, what if life is not actually that simple? What if it's not actually a simple problem hiding in a large dimensional space? What if it actually is a function of a lot of variables? And there's some more recent work doing this with deep networks, modeling the space with deep networks. That looks promising because of how it handles the dimensionality. The problem with that, of course, is that it's notoriously difficult to get reasonable confidence intervals out of deep networks. And so it's hard to make good experiment decisions when you use that approach to it. But it is something that's being tested. What we're going to do is something a little bit different. We're going to say, okay, we don't want to say this is just a low-dimensional problem hiding in a high-dimensional space. But is there some other structural assumptions that we can add to this problem that's going to make it tractable for us? And the one we're going to add is we're going to assume that function we're trying to optimize is additive. So in this example here, there are 10 variables. So this is a 10-dimensional function. But we're going to imagine what it really is this function is the sum of 3 functions of 3 variables. So the green variables 1, 3, and 9 make up one function. 2, 4, and 8 make up another function. 5, 6, and 10 make up another function. And the real one is the sum of these. So, and 7 just happens to be ignored. So this really is a 9-dimensional function, but it's got a little bit more structure to it. So that's our plan to scale up the dimensionality here. Okay, this slide full of math, don't look at all this. There's only one point to this slide full of math, which is it just says that Gaussian processes still work. If you have this kind of function, you can observe just the inputs, all 10 input variables, and the single output variable, and you can still do the inference. You can estimate all the component functions and your uncertainty about all of those component functions. And so, great, we can still proceed with this kind of model using Gaussian processes. Okay, so what does that mean? What does that look like? So here's let's try to put this in pictures. Here's a simple one. We have a 2D function of just 2 variables, but each one it's decomposed. It's the sum of 2 1D functions. And so if you look at this here, you see the 1D functions on the side and bottom. And of course, when you add them together, you get this 2D contour plot that's in the middle. So great, okay. And I put some X's there. Suppose you observe some points. And this is just a visual illustration of what I already said. You can still do all the GP math. What you get is estimates of the 2 component functions, and you get estimates of the uncertainty around those 2 component functions. So far, so good. And so now what we're going to do is propose a new acquisition function here. And this is one that all it does is runs the acquisition function on the components and then uses that to do the selection. So that looks just like this. You separately pick the coordinate for one and the coordinate for the other. And so the good news about that is because you're optimizing the acquisition function just on those component pieces, optimizing that only scales exponentially in small d, which is the size of the component functions. So now you have something that you can actually do the optimization to choose your model. And so where does this bring us? This is for the squared exponential kernel, but these results can be done for other kernels as well. If you just do GPU-CB on a whole space, the number of samples you need is exponential in the dimensionality of the whole space, exponential in capital D. But now if you do this decomposition here, small d is the size of your component functions, how many dimensions they have. Now it turns out the sample complexity is only exponential in the size of those small components, in small d. And of course, as I just said, you can also optimize the acquisition function in time that's only exponential in small d. So this allows you to go up to higher dimensions. Okay. The next question is, okay, that's great, but what if these high dimensional functions aren't really, I complained earlier, what if it's not really a low dimensional function hiding in a high dimensional space? What if the same thing happens here? What if the true function is not an additive model like I've shown here? It turns out, I'll show you some experiments, it turns out that this is now an intuitive statement, not a theoretical one. It turns out that because of the bias-variance trade-off, you can often optimize the functions better if you have simple additive models, even if they weren't accurate models of the function. It's quite nice that way. And so I'll skip this. This basically says there's MATLAB code for this if you guys want to try the the additive models. So we started with some synthetic functions. So we actually created additive functions. So we knew where the optimum was and what the structure of the space was. And so what do? The nice thing happens here. So this is an example. It's the one I showed you. There's 10 dimensions all in the whole space, but it's really the sum of three-dimensional functions. And what we find out, you can see some comparisons there. The random algorithm just chooses experiments at random. Direct is a classic old one that just divides the space by rectangles. GPUCB is just running the plain UCB algorithm on a Gaussian process. And then you see various examples here. And the cool thing about this one, the one on the bottom, so this is showing regret, so lower is better. The one on the bottom, add star, that's the one that knows the decomposition. It knows there's 3 sets of 3 variables and it knows which variables they are. So of course that one does the best. But it turns out if we just did some other decompositions that are low dimensional, even those beat the GPUCB algorithm and the random algorithm and the other ones. This happens again in a higher dimensional space. So here's one that's 2 18-dimensional functions together in a 40-dimensional space. The interesting thing here, of course, all these models beat GPUCB, direct, and random. Those are hopeless in 40-dimensional spaces. What's interesting is add star knows the decomposition. It's 2 18-dimensional functions. It gets beat by simpler decompositions that are wrong, that are not the actual decompositions of the space. So that's kind of it's kind of an observation of what I just said there, that having a simple model can help you do optimization. Of course, we don't want to do just synthetic examples. We want to do real examples. So here's one from science. There's a bunch of cosmological parameters. We see observations from telescopes. And what we would like to do is run an expensive simulation where we guess what the parameters of the universe are. We guess how much dark matter and dark energy and what's the shape of the universe and all those other things. And then we run an expensive simulation, right? It's expensive because you're integrating a bunch of differential equations. And what you do is you plug your guesses in, you run the simulation, it gives you simulated observations of the universe, and then you compare them with what we actually see in a telescope and try to decide whether those guesses were good or not. So this exactly sets up this problem of expensive simulation that you have to pick parameters for. And so what we see with this is, again, the same thing. So now there is no add star here because we don't know that this function's probably not even additive. We're just guessing. So we just tried some examples of these. And here it's, sorry for my graphs being upside down, but this now higher is better. So this is how well it fits the observed data. And again, all these additive models, none of which could actually be the correct models, are all beating the regular Gaussian process, UCB, expected improvement, random experiments, all of these. Just to show you another one, so the classical Viola-Jones face detection. Everybody knows this, a cascade of classifiers. There's lots of decision thresholds on all of these. So we can do the same thing here, and the same thing happens. This additive algorithm is able to beat all the competitors, even though we don't have any way to know the decomposition if there is one. So, okay, great. Additive GPUCB, what's the current state? It's improved the regret theoretically from being exponential in capital D to being linear in capital D, and it's now only exponential in small d, the size of the components. Even when f is not additive, it seems to do well, and it's computationally efficient. There's lots of open questions. One is how to choose the decomposition. If you don't know it, what are you supposed to do? Another one is how do you handle non-axis aligned models? And then the last one's the one I really want to talk about is multifidelity optimization, but let me just skip through a couple of the others just so you can see they're there. So it turns out, what if you don't know the decomposition? It turns out a very good idea is just choose one at random on every iteration. Sometimes you'll get it wrong and you'll effectively do a random experiment. Other times you'll get it right and you'll make a smart experiment. And overall, it works. If you feel insulted by picking decompositions at random, what you can do is estimate the likelihood of all the decompositions, do a lot of them, look at the likelihood, get a distribution over the decompositions, and each time take a sample from that decomposition. And that, again, that should have the property that you get more good decompositions more often. That one also does quite well, although it's unclear it's better than just picking them at random, at least in some of our experiments. So I'll skip over that picture. That just says that. Another thing that you can do is maybe your decomposition is not nicely axis aligned the way I've drawn it, where you assign variables to different pieces. Maybe it's actually some rotated subspace. This turns out, this sounds like an easy idea. The math is kind of easy. It all works. There's just one really bizarre thing that is hard to do. Once it's rotated, it's hard to do the optimization of that additive function, because the value that you choose in one dimension impacts which values are valid in the other ones. And it sounds like, man, that shouldn't be hard, but it actually is hard. And we've done some things to try to constrain the rotation a little bit that look promising, but I regard that as still an open problem. We have some results on that, but what I really want to do is skip to multi-fidelity optimization. It turns out that, okay, this is great, we're being pretty efficient, but still experiments are expensive, and often you can do cheap approximate experiments to give you an idea before you really do the full-blown experiment. So if you think about, for example, deep learning, what do? You're trying out some new architectures. Nobody throws their whole data set at the crazy idea they have, right? You choose some small data set, you get a few cross-validation results, you get some ideas about whether it might work. You search around that space for a long time before you go off and kick off some job that loads down your whole cluster for a month to see if it's good or not. And so the idea here is, well, if that's how people do this, how do we get an algorithm to do that? So that we can be smart about even that process. And so what does that look like? So I've gone back to just looking at, so think of this as a bandit problem. There's 10 alternatives here. And what you can do is think about the blue hashes as that's the mean return of this bandit for your low fidelity optimization. So it's not quite right, but it is related to the real one. And the green bars, those are the real evaluation. That's the thing you want to optimize. And so that's our setup. And of course, the blue ones, it's cheap. The blue ones cost lambda 1, and the green ones cost lambda 2. It's cheap to do experiments on the blue ones and expensive to get experiments on the green ones. How are we going to optimize this thing? Okay, there's another example. Okay, here's what we do. What you can do is for each fidelity level, you look at all the experiments you've done on that arm for that fidelity level, and you get a confidence bar, right? So you're going to look towards a UCB algorithm. You want the confidence band on that. You do that so for the high fidelity one, you have your regular confidence bar. For the low fidelity one, so this is the one that's B1 in the upper left corner, you have your confidence bar plus some other constant, which is the limit of how much difference there is between your two fidelity evaluations. So you have to add that into your uncertainty. If you take low quality evaluations, you've got this extra factor about what the real value is. So it turns out now you can do a simple algorithm. You've got two estimates of the confidence bar for particular alternatives. You just take the tighter one, whichever one's tighter. They're both confidence intervals, and you assign that to the arm. And then you run UCB to pick an arm. And then now you've picked an arm. Now you have to make a decision. I'm going to test this arm. Am I going to do the low fidelity, or am I going to do the high fidelity experiment on this? So there's a couple ideas. If you want to be able to do theoretical analysis of that, I recommend you set a threshold on the width of the low fidelity arm, and once it gets inside that, then you switch to the high fidelity arm. I recommend that if you want to do theoretical analysis. If you just want something that works well, I recommend a heuristic which just says which fidelity level would be expected to make this no longer the arm I want to choose with the lowest amount of cost, given the cost of each one. Turns out that one works very well. And so my apologies for all the small print. Basically what this says is here lower is better, These are log scales. That ugly black curve at the top, that's a standard UCB algorithm. It's very expensive. The ones below that are what you get if you run this algorithm with different values of gamma. And the red curve buried in there is that heuristic I just described that can optimize this function at, again, these are log scales. So these are a lot lower cost than if you just ran the algorithm naively. I mentioned theoretical results. If you're interested in them, there's 2 papers coming up from Sammy in NIPS this year. So you can look up those papers and see how you do theoretical analysis of multi-fidelity algorithms. Let's see if I have enough time for this. So at ATC, we have our own Bayesian optimization engine. We're setting up just what I described to you. It runs experiments in parallel through a cluster, and it selects points using some of the methods I just described to you. Just as one fun example, what this is, oh, sorry, that's the synthetic ones. We don't want to do that one. Here we are, one of the many things we might like to optimize. Here's a pedestrian detector. It's used gradient boosted decision trees, and there's hyperparameters of this we might like to optimize. So we went ahead and did that. This is a 6-dimensional optimization. And what those 2 curves show, sorry, the print's kind of small, but I'll just tell you what's in there. We wanted a high detection rate, and we wanted small trees so we could execute them really fast in real time. And what we showed is that with about 280 evaluations and about 100 hours of real clock time on a cluster with 200 cores, we were able to make substantial improvements, a little bit in the accuracy, but a lot in the complexity of the trees. So what's the summary here? We're going to automate the optimization of systems. They're just too complex to do by hand, and it sounds a little scary to have that done. But you know, it's not really different than classical engineering anyway. Any of you who have been involved in engineering efforts on big complex systems realize that this is happening anyway. Different parts of the system are being tuned separately, and you're constantly being undermined by changes other people make in other parts of the system. So I would claim it's not any scarier than what's already happening. Let me skip ahead to the summary slide. You know, robotic autonomy is coming in many forms, and active optimization is the only way we're going to get these complex systems working. There's lots of problems left to solve. One I did not even mention, and I think this may be the hardest one yet. So if any of you wants to solve this, that would be great, and please let me know. Here's the problem. I just said, okay, you have a high dimensional space, and we'd like to optimize this. And okay, great, let's go off and run the optimization. But that's not actually what happens. What happens when you're building a system is you have a high dimensional space, the experiments are not going well, and someone walks into your office and says, I have an idea, let's tack this thing onto it with 2 more parameters. And you say, okay, so you try that. And then someone else shows up with 2 more parameters. And so you have this weird situation where you're accumulating experiments where the parameter set is growing as you go. And you need a smart way. You still want to carry over what you learned from your old experiments, but the parameter set is growing as you go. And I think that's an interesting and hard problem to challenge. I think it goes without saying that Uber is hiring, but I'll say it anyway, and thanks for listening.
Question?
Have you tried to use PCA or sparse PCA to group your variables? Mm-hmm.
Yep, I think that's it's a good idea. It's one that people do. It's actually a kind of common one that people use when they're faced with exactly this. They say, I've got too many variables, I can't search this space. Is there some way to use PCA to reduce it? The challenge with using PCA, of course, is that it makes the reduction based on the distribution of the points in the space. But in this case, that distribution doesn't have any real meaning. It's just the distribution of the experiments you've chosen to run so far. So it's not clear that you're going to get the right smaller space. Yeah.
Doing the variable grouping. So if you
Uh-huh, yep, 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 you can definitely try that, yeah, yeah.
Thank you for the talk. It was great. Could you give us a little bit more intuition on why knowing the decomposition is actually performing worse than just, you talk about the bias variance trade-off, but
Yeah.
could you talk about it a little bit more?
Yeah, sure. It sounds a little bit counterintuitive, but the easy way to think of it is, let's think of a real system. We have these, everybody who's building systems has this all the time, right? There's 20 parameters in there. What do you actually do? And it probably is a real function of all 20 parameters. What do you actually do? You say, well, that's just too many. Let's fix them all at a variable I understand, and let's pick one of them and do an experiment. See what happens if I turn this one up. And let's do another experiment where I turn this one down. Okay, I found a new spot. Let's set them all to this. Let's check some others. I mean, this is what people actually do, right? They just can't handle it in the large dimensional space, so they look at low dimensional subspaces and they sort of optimize them one at a time. And in fact, it's not a terrible idea. I mean, systems are built that way, and I think that's the intuition. The reality is, no matter how fancy my algorithm is, if I'm still trying to optimize a 40-dimensional space with only a few hundred experiments, I just can't do a 40-dimensional space, right? Even if the true decomposition is 40. And so what you saw on my graph is what happened is it was a 40-dimensional space that was really two 18-dimensional functions. So even 18-dimensional functions are really big if you're only going to do a few hundred experiments. And so that's why we saw that result.
One more.
So splitting it up into a series of distinct additive functions is nice. What about overlapping those additive functions? So actually saying we're going to use variable x in function A, B, and C and do a nice, combinatorial blend of those.
Yeah, I think it's a great idea. We thought about that, and it turns out at least the Gaussian process, that doesn't cause any severe problems doing that. The problems you get from that is optimizing the acquisition function. Now you have these overlapping acquisition functions, and you lose this property that you can run the acquisition function on each of the components separately and just compose them. Now you have to do some joint optimization of them. Not saying you shouldn't try it. It just means you've got to somehow, and we haven't tried it yet for exactly this reason, but you've got to come up with something a little bit cleverer to do that connected optimization. Yeah.
Great. Okay, thank you, Jeff. We are on break.